Hello friends, this is my YouTube channel Fact Stack. Please subscribe my channel and press the bell icon to get more informative video. In this video we are going to talk about the general relativity. Looking back at 100 years of general relativity, one may ask how has general relativity changed the world? The answer can be seen everywhere in the cosmos. It was for almost 250 years gravity was regarded as an attractive force that holds the universe together, till the German physicist Albert Einstein came up with a better explanation with his general theory of relativity in 1915. Einstein showed that gravity is not a force but a consequence of curving space-time. In other words, the popular idea about gravity from everyday experience does not hold water. General relativity changed the entire concept of how the universe works. Gravity is so ubiquitous and so familiar to us that we hardly ever give it a serious thought. When anything falls from a height or something topples, we take it for granted. Scientists consider gravity as one of the four fundamental forces of nature, the other three being electromagnetism, weak force, and strong force. The uniqueness of gravity that sets itself apart from the other three is its universality. It represents the universal tendency of all matter to attract all other matter, and it is an effective over extremely large distances. It is also the weakest of the fundamental forces. We learned in the school that the English physicist Isaac Newton discovered gravity in 1666 after observing an apple fall in a garden, and that he also concluded that the same force also keeps the moon in orbit around Earth. His detailed work on gravity was published in Principia Mathematica in 1687. Newton presented gravity as a pull to Earth and later in a more generalized way as a force of attraction that acts universally between any two masses, and the set strength of which is proportional to the product of two masses and inversely proportional to the distance between them. Einstein made several unsuccessful attempts between 1908 and 1914 to formulate a theory of gravity that was consistent with special relativity. The German physicist Max Planck is said to have told Einstein, "As an older friend, I must advise you against it. You will not succeed, and even if you succeed, no one will believe you." Never want to yield to authority, Einstein proved him wrong. In 1915, he came out with a general theory of relativity that could answer many questions. Newton's theory could not. It revolutionized our concepts of the universe. The special theory of relativity is valid for systems that are not accelerating, which means it is valid only for situations where no force is involved. Since gravity involves acceleration, which involves a force, the special theory of relativity cannot be used when there is gravitational field present. In the general theory of relativity, Einstein tried to remove this restriction so that he could apply his ideas to the gravitational force also. But the task was not simple, and it took Einstein almost 10 years to fully understand how to do this. In the general theory of relativity, Einstein was attempting to formulate a new theory of gravitation in place of Newtonian gravitation. His goal was to find the mathematical equation describing two interwoven processes, namely how a gravitational field acts on matter, telling it how to move, and second, how matter generates gravitational fields in space-time, telling space-time how to curve. The struggle Einstein had to face in trying to find a mathematical model to explain gravity incorporating these two was really daunting. For more than 3 years, Einstein tried hard to formulate drafts and outlines that turned out to have flaws. Then, beginning in the summer of 1915, the math and the physics began to come together. By late June 1915, many elements of general relativity were almost ready, and Einstein decided to give a week-long series of lectures later that month on his evolving ideas at the University of Göttingen in Germany. Foremost among the learned audience was the German mathematician David Hilbert, and Einstein was particularly eager to explain all the intricacies of general relativity to him. As he told his friend later, he was quite enchanted with Hilbert, and he was able to convince Hilbert of the general theory of relativity. Hilbert was likewise enchanted with Einstein and with his theory, so much so that he soon set out to see if he could do what Einstein had so far not accomplished: produce the mathematical equations that would complete the formulation of general relativity. So a race was on. By early October 1915, Einstein started worrying about Hilbert's attempt to work out general relativity, just as he realized that his current version of the theory, which had been refining continuously, still had serious flaws. His equations did not account properly for rotating motion, nor did they fully explain an anomaly that astronomers had observed in the orbit of the planet Mercury. In fact, they could sense that Hilbert was closing in on the correct equations. He decided to give a series of 4 formal Thursday lectures on his theory to the members of the Prussian Academy in Berlin. Beginning 4 November 1915, the result was an exhausting month-long rush of activity, during which Einstein wrestled with a succession of equations, corrections, and updates that he wanted to complete. Finally, on 25th of November 1915, Einstein delivered the fourth to the last of the Thursday lectures to the Prussian Academy of Science, in which he presented the final version of his gravitational equation in a paper titled The Field Equations of Gravitation, in which he wrote, finally, the general theory of relativity is closed as a logical structure. The general theory of relativity combines special relativity and Newton's law of universal gravitation, providing a unified description of gravity as a geometric property of space and time, or space-time. It characterizes gravity not as an innate force acting on objects, but rather the consequence of space-time's curvature. It was a hard-fought battle. 5 days before Einstein made his presentation to the Prussian Academy of Sciences, Hilbert had submitted a paper to the Gesellschaft der 7th Royal Scientific Society in Göttingen, which contained the identical field equations but with one small difference. But Hilbert never claimed priority of his theory. Abraham Pace, biographer of Einstein, wrote in subtle Is the Lord, the Science and the Life of Albert Einstein. I do believe that Einstein was the sole creator of the physical theory of general relativity, and that both he had and Hilbert should be created for the discovery of the fundamental equation of general relativity. The theory exposed it as a simple consequence of the geometry of space and time. It established space and time as a single entity, space-time. It launched new strands of research that scientists are still pursuing and made it, its creator, a star. In this theory, Einstein described what happens when mass is present in space-time, causing it to curve and forcing objects traveling through it to follow a bent and longer path. If enough mass is packed into a very small region, space-time becomes infinitely curved, creating a black hole. After that, there was a period of testing the general relativity. The first test of Einstein's general relativity came in 1950 and involved Mercury, the planet closest to the Sun. Like the other planets, Mercury also moves around the Sun in an elliptical orbit, with the Sun at one of the foci. The point of closest approach to the Sun is called the perihelion. Normally, according to the Newtonian physics, one would expect the orientation of the orbit to remain unchanged. That is, the perihelion should stay where it is, as it does for all solar system planets except Mercury. More than a century later, in his general theory of relativity, Einstein calculated that the reflection predicted by his theory would be twice the value calculated by Solner. But the experimental proof was yet to come, and the proof finally came from the British astronomer named Arthur Stanley Eddington, who was the then Secretary of the Royal Astronomical Society. When Einstein presented his general theory of relativity to the Prussian Academy of Sciences in 1915, Eddington was in England. At that time, Britain and Germany were at war, so there was no direct scientific communication between the two countries. But the Dutch mathematician and astronomer Willem de Sitter, who was in Holland at that time, was Eddington's friend, and he passed on a copy of Einstein's paper to him. After reading the paper, Eddington was immediately aware of its rarefactions, and in the report of the Royal Astronomical Society in early 1917, he particularly stressed the importance of testing the theory using measurement of light bending. The upcoming total solar eclipse of 29th May 1900 afforded an appropriate occasion to the test of the theory. A few weeks later, then the astronomer Royal Sir Frank Watson Dyson decided to send two scientific expeditions to observe the eclipse. One led to Eddington was to travel to the principal island of the coast of Spanish Guiana in West Africa. The other expedition led to Royal Greenwich Observatory astronomer Andrew Crommelin was to travel to Sobral in northern Brazil across the Atlantic. On 6 November 1919, 4 years after Einstein announced his general theory of relativity, newspapers the world over trumpeted the just released astronomical measurements, establishing that the positions of stars in the sky around the ellipsoid sun did appear slightly different than that Newtonian physics had predicted. Rather, it was just as it ought to be according to Einstein's theory. Eddington's results conveniently confirmed Einstein's theory and turned him overnight into an international superstar. Thanks for watching.